Okay, let me quickly go over this. So the important point of view is to linear algebra is broader and just looking at everything as a function. So because you go from dimension 1 to 2 to 3, and then where's the end to it, and then, well, you can't really rely entirely on matrices to help you thinking about what's going on. We're talking about functions. And so that's where things like compositions come from. Okay, so just compose functions in the usual way, consecutive functions, and consecutive applications of functions. Then that's also where the idea of the inverse comes from. It comes from the same exact place. So it's not linear algebra concept. It is what is it? Call it. You can think about as a pre-calculus a concept or set theory concept, and then then from there, not from linear algebra come things such as what kind of function has the inverse, and that function has well, first of all, the definition of the inverse is the composition. Secondly, what kind of function has the inverse? It's a function that is a bijection, one-to-one onto, or one-to-one correspondence. And that also, well, this is the definition. And only then we go back to linear algebra to actually add specifics to what we're talking about, and, for example, find some of the inverse functions. So we did. Sometimes it's easy. I mean, if you have a rotation, you can say that what its inverse should be. If you have stretch, you shrink. You have shrink, you have stretch. Rotation. The opposite direction flip is the inverse of itself. Two flips, you come back. So things that are easier to understand if you think about these as functions rather than special kinds of functions rather than special kinds of numbers. So we speak of algebraic operations on matrices, but really then if you might think about them as kind of special kind of numbers, they are more like they are more like functions. They are functions. Okay, so rather than doing it from scratch again, we have a few examples already. So we could just go straight ahead and find the inverse explicitly. In the general case, we did something like that already. A is equal to A, B, C, D. So we just write it out. So let's suppose, suppose A inverse is some matrix X, Y, U, V. Okay, and then we go straight back to the definition and write it out. Definition is I'll take A inverse and I put them together, right? So I have A, B, C, D, and I have here X, Y, U, V. Okay, and that is these two matrices multiplied by each other is supposed to produce the identity matrix, which is 1, 0, 0, 1. Okay, solve for X, Y, U, V. Okay, so what would you call this? So we need to find the inverse, which is a matrix with 4 entries, and so then I just wrote half of the definition I wrote here. Now I need to find those numbers x, y, u, v. So what is it? It is a system of equations. It is a system of equations of dimension, no, 4, that's right, it's 4 unknowns. Dimension suddenly becomes 4. Okay, so if I just multiply, for example, I'll have in fact 4 equations, 4 unknowns, as you'd expect. So I have ax plus bv is equal to 1. Then I go ay plus, hold on, this is a u over here. Ax plus by, first row, first column, ax plus by is equal to 1. I move to the right. I have ay plus bv is equal to 0. And then second row, I'll have, cx plus dy is equal to 0, and finally I have what cy? No, cy. Okay, no, first row, second row, second column. Second row, second column, right? cy plus dv. Oh, yeah, but maybe the third one is wrong. This is one. Cx plus du, not y. Okay. Du. Okay. So, indeed, just for practice, I could actually write out the augmented matrix, or well, matrix. Let's write matrix equation. So, what is it? My coefficient matrix is A 0, B 0, 1. Well, let's go with the. I'm multiplying it by x, y, u, v, and it is equal to 1, 0, 0, 1. The order certainly matters, but we could rearrange it if we want to. Then I have 0a, 0b, c, 0d0, and 0c, 0d. All right. Okay. System of 4 equations. So to resolve the issue in 2-dimensional linear algebra, we need 4-dimensional. Okay, so no surprise. It doesn't look that complicated. You don't have, as always, with small systems, you don't have to deal with systems. You don't have to deal with matrices. But it is, what I mean is that you solve it any way you want to. But we're learning this because ultimately somebody else. And somebody will be doing it, and somebody else, that is a computer. So computer will be doing it for you. So we just do small ones for practice, just to get a feel for it. So I'm not gonna even do it. I have the answer right here for A inverse. It is it's not easy, even though it has a bunch of zeros, so it makes life easier. But there is some computations. There is at the end there is a factoring, which is very convenient. Fortunately, all the terms will be available. So it will be AD minus BC as you'd expect, as a factor, and then there are these coefficients. So as you can see, so that's my inverse matrix. X, Y, and U and V are those fractions. So with the numerator, these are the numerators that are in the matrix, and the denominator is the same. Fortunately, it is, in fact, what is this? The denominator, the determinant of A, right? Okay, and as to be expected, because what does the determinant determine? It determines whether or not the function is the matrix is invertible. So determinant is equal to not equal to 0 if and only if A is invertible. That applies to all dimensions of square matrices, except we haven't defined what the determinant is yet. We only know two-dimensional, but well, it is pretty much the goal for the determinant. But this works out pretty nicely. Remember, that's how the determinant came up. We were trying to solve a system of equations once and for all, not finding the inverse, but solve a system of equations with A, B, C, D coefficients, and we ran into the determinant. Okay, and so if we try to solve a bigger problem, and that's simply finding the inverse once and for all, we once again naturally run into the determinant, and now it is very explicitly there giving us the answer for the inverse. You certainly need to verify. What do you need to verify? We solved the equation. What do we need to verify, if anything? The second half of the definition, which is A inverse A is equal to the identity. Okay, so all right, or not. I mean, you don't really have to verify it if you're comfortable with the set theoretical approach. Then you don't need to verify anything, because we know that if the universe exists, it is then it is if the well, what am I saying here? Well, you have to know whether or not the function is one-to-one, whether the function is a bijection in the first place. Then you don't have to verify both of the conditions, just one. Okay. Anyway, that theorem is what we want to have in high dimension than that. Right now, we are done with dimension 2 almost, with the exception of eigenvalues and eigenvectors. But I want to make at least a small step in the direction of dimension 3 and higher, and to at least point out what our what the meaning of the determinant is in dimension 3. With the same plan, that the plan has to work out in any dimension. So we only have demonstrated that this is indeed the case for dimension 2. For dimension 3, we don't know what the determinant is, but we probably could guess what it is if we just compare, go back to our examples of matrices, which are pretty much here, and ask ourselves what the determinant might be telling us about it. And one thing is, one thing is, as an example, once again, 2 and 3. Its determinant is, so once again, AD minus BC, just to remember what it is. So it will be 2 times 3 minus 0 times 0. So it is 2 times 3, which, as you can see, the two coefficients that stretch our the multiples, the two coefficients that stretch in the horizontal and vertical directions of our plane. They get multiplied. That's what determinant is, then the product of those two coefficients. And that is, in fact, to a degree correct, should be correct in all dimensions higher than that. So, for example, we would probably expect to have something like this. Like this. If I have a matrix 3 by 3 this time, it should give me 2 times 3 times 5. Okay, so a diagonal matrix will have, think about it, a diagonal matrix is very simple, and it is clearly what it does. It does the stretching in these in 3 particular directions along the axis. Imagine that one of the, but what if one of the diagonal elements is 0, then what? 2, 3, 0. What is this? Stretch along y, stretch along z, stretch along y, stretch by 2 along the x-axis, stretch by 3 along the y-axis. What about z? How do you describe the stretch? What? It is a point, but what does it do? What does the what? No, it's not. It's not nothing. It's a lot. It collapses. It collapses along the z-axis. So stretching, shrinking in these two directions, and then like this. So a three-dimensional space ends up on the floor. The whole this space is collapsed into the floor. And then, no surprise, then if we think of, if that's our guess, is that the determinant should be, for a diagonal matrix, should be a product of the 3 diagonal elements, then the determinant is equal to 0, and that's a good thing, because, once again, this is what we're trying to accomplish. We want to define the determinant in such a way that determinant equal to 0 indicates that the matrix is not invertible. And this matrix, the collapse, this is the collapse, it is not invertible, right? It does not have the inverse because, well, it's not a bijection. So because of the collapse, many points end up at 0 and other places. So there is no inverse, and that works out fine. The first example, this is a stretch, non-uniform stretch in all directions. determinant is not equal to 0, so it works out fine. It is a bijection, and the determinant is not equal to 0. Great. So once again, it works out fine, at least for the diagonal matrices. It appears to be okay. Then also the another example would be beyond stretches would be flips. Okay, it's slightly more complicated, but once again you can have, say, well, this is one example. It is the negative ones. The present of negative 1 reverses the orientation of that plane, and but if you have you have 2, then what happens is the orientation is preserved, because negative 1, if I'm talking about this 2 by 2 matrix. Remember what it is. It is a flip. It is not. It is a rotation around the origin. Okay, which means rotation does not reverse the orientation. So if you have a circle going clockwise, it will still go in clockwise. Okay, but if you have only one negative 1, it is a flip. It is a flip this way, and then it reverses the orientation from clockwise to counterclockwise. In 3D, it is more complicated because now we have 3 x's, and once again you can do all kinds of flips. And what this operation is, you go and carry out 3 flips about the not x's this time, but about the coordinate planes. So you flip it about the xy plane, yz plane, and xz plane. And then does it reverse the orientation? Every flip reverses the orientation. So if you do it 3 times, you still reverse the orientation. Okay. So, but if you do it twice, you go back to the same orientation. Okay. So in dimension 3, it's more complex because you cannot speak of circles going clockwise. You have to speak about what. Remember what this about the orientation in 3D, the right-hand rule. So that's what we're talking about. So you go from x to y with your fingers, and then this points in the z direction. Okay, so that's the orientation of our space according to Cartesian system, the standard Cartesian system. But under 3D transformation, it might reverse to the opposite. So if I flip our 3-dimensional space in the mirror image, in the mirror literally, my right hand will become the left hand, right? So that is the reversal of orientation in dimension 3. Okay, so literally the right hands become left and vice versa. But that's when you have 1, negative 1, you have 2, you do it twice, and then right hand comes back to right hand. If you do it 3 times, you have again a reversal of orientation, and once again you have right hand has become the left hand. Okay, so that is the good thing about the determinant. It not only tells you whether or not you have a bijection or not, but also the sign of the determinant tells you whether or not you have what happens to the orientation. So is there somewhere flip or not? Because flip is the only thing that of those operations that we know that reverses orientation. When it is 0, then there is no such an issue, right? Think about it. Right hand, and when it collapses on the floor, well, what's left from the orientation? Nothing. Okay, so those non-bijections are just a special case of when the orientation is not preserved, no, it is reversed. It is just what happens. It's gone. Orientation is not an issue anymore. So the only thing that we can take into account, try to figure out what the 3-dimensional determinant is supposed to look like, is once again looking every time at the 2-dimensional pieces or blocks in our 3D matrix. And so we did it twice for stretches and for flips. Rotations are more complicated if you think about it, because we can rotate even the simplest one. Rotations about each of the 3 axes would be kind of complicated. So I'll just give you the answer once again for some just practice to compute it a few times. So it is expressed in terms of, if you've taken Calc 3, you know the answer, but here it goes. If I have my matrix A, B, C, D, E, F, G, H, I, okay, so that is my matrix, and I want to compute its determinant. I go along the row or the column like this. I remove the first row, and then of what's left, I'm left with 6 entries, and what's left is a matrix 2 by 3, okay? And from that matrix 2 by 3, the second 2 rows, the second, third rows, I can extract 3 different 2 by 2 matrices, okay? And and then those determinants will be used for that. So this is the number 1. So I have that's not the first one actually. The first one is this. So it is E, F, H, I. Then here I have removed the first column. The first row is removed altogether, okay? And then I am removing the first row, and then I'm left with E, F, H, I. If I remove the second column, I'm left with D, F, G, I. And finally, if I remove the third column, I'm left with D, E, G, H. Okay, and then the coefficients are A, B, and C. So I start with A. As you can see, how do I explain the first term? I take A, write it up there, and then I remove the column and the row that contain A, which means that I remove the first column and the first row, and that gives me the matrix EF. I forgot the crucial part. We're talking about the determinants here, right? So this is determinant. Okay, and here I have, as I said, A, B, and C. So for the second term, I concentrate on B. I write B, then remove the first column that it contains B, in the second first row it contains B, and then the second column, and I'm left with GF GI, right? Yeah. Well, maybe I could. The only thing that I wanna that is missing is the signs alternate. So that's shouldn't be entirely surprising. But let me do it once again. What I just did. So if I take this and paste and paste. And paste. Okay, so I start with my original matrix, and then okay, so this is the same matrix, and then I remove one row, the same row, and different column at a time. So this is what I do. I remove this, and that. You see how I'm moving from left to right, and at every time I'm left with 2 by 2 matrix. So this is 2 by 2, and here I left 2 by 2, and here's also 2 by 2, and I write them over here. I take those determinants, and then the coefficients will come up also. So as you can see, this is the what I'm concentrating on, like this. So as you can see, the formula for dimension 2 was not that easy. It had 4 numbers, and we actually ended up multiplying them in a somewhat complicated crisscross manner, right? So so determinant of in dimension 1, dimension 2, A, B, C, D is equal to AD minus BC, and it is a cross multiplication like this minus that. Okay, so it is not that easy to begin with, and then dimension 3 you have, instead of 4, you have 9 elements, and they are certainly combined together in a complex way. What is the similarity, besides what we are looking for, the special kind of a characteristic of a matrix? The similarity is, let's see, for example, every term appears exactly twice. Every term of the matrix appears exactly twice. Exactly twice, yes. It appears exactly once in the original one, and here we have more and more accumulation. So the units are, instead of 2, it becomes 3. Right, so you only multiply A by D, so that's degree 2. You'll have degree 3 here, because if I keep writing out what I'm going to have here, I'll have E times I. So it will be one of the very first term will be AEI. What is AEI? It is actually the product of the diagonal elements, what we just talked about. Okay, so the rest of them are kind of appear in a kind of a random way, but not entirely. So that is certainly how you can reduce the definition of a 3D determinant to 2D. But if you want an explicit formula, which is just, it's not really that impressive, I suppose, if you, it just for dimension 3. So let's see, these 3 plus these. Is it clear what I'm doing here? I'm multiplying entries. So one entry is the diagonal 3, then I'm multiplying these 3 like that. And then I multiply those 3 like that. So that these are the 9 entries of my matrix, and that's how I'm multiplying them in such a weird way. And that's only half of it. Right? Then I reverse it. And that is, so that's where the minus sign comes from. So positive followed by negative, like this. So I have, once again, these are my 9 entries in the 3 by 3 matrix. And then what do? I take these first, and then I take those, like this, and finally these. Okay, so as you can see, once again, every term appears once in the first half, and then appears once in the second half. So every time, everyone appears with plus or minus. And then exactly how many terms? 6 terms, right? So that is, since the time is short, going into high dimensions is somewhat complicated. You can see dimension 3 is already complicated. So the determinant is, however, every computer, every programming language has determinant as a built-in function. So it is actually probably more important to actually get a feeling for the determinant than to actually do it computations by hand. I would still encourage you to compute it this way a couple of times. Let me do it once, but there are certainly more important things. So say 1, 2, 1, negative 1, 0, 1, 1, negative 1, 2. Okay, so how do I compute the determinant? I can do it in 2 ways, as I just indicated. Let me go with this first. So I'm going to go diagonally. 1 times 0 times 2, diagonally. Okay, then I go this triangle that is facing northeast. So it will be 1 times negative 1 times negative 1. Okay, you see what I just did, this one? And the third term is what's left. So I start with the diagonal. the main diagonal, then I go the missing elements, and finally I'm going with the with these. So it will be the triangle that is the pointing in the opposite direction. So it will be 1 times 2 times 1. Okay. So these are the ones that is the blue terms. The blue terms that come with plus signs, and the rest will come 3 more terms with negative signs. The diagonal, the other diagonal, it will be 1 times 0 times 1. Okay. Then I'm left the triangle pointing in that direction. It is 1 times negative 1. And finally, the triangle that points in that direction, so it will be 2, 2, negative 1. Okay. Okay. So 0 plus 1 plus 2 minus 0 plus 1 and plus 4. So it is 8. Yeah.
The third, like addition 1 times 2 times 1.
Yeah.
What is the triangle for that?
Here it is. This. Okay, so it appears to be 8. I could now do it the other way with the definition that is we are looking at right above. So let me recalculate. Well, any questions about this computation? So yeah, getting complicated. It is about permutations. In case you didn't get that, anybody of you has taken like a probability or combinatorics, anything like that. So it is about permutation, careful permutations of elements. So look at it, each of the terms, once again, if you look at the picture on the left, each term contains 3 elements, 1 element from each column, and 1 element from each row. So there is a system there. Well, there is certainly a system there, even though it looks totally random. But it is all possible permutations of in that manner, of elements done in that manner. Okay, so in how many ways can you pick 3 elements in such a way from this matrix in such a way that 1 per row, 1 per column? And the answer is 6. You can do it only 2 ways with 2 by 2 matrix, and that's why we have only 2 terms. We have 6 ways to do it, to do such a permutation in a 3 by 3 matrix, and then it certainly grows. Okay, so let's do it one more time. We're using this definition. Okay, so carefully. Let me do it carefully. So I'm going to be writing 1 by 1, going across the top row, and then hopefully we'll get the same number. So I'm doing the determinant 1 times the determinant of what's left, which is 0, 1, negative 1, 2. Okay, minus. Remember alternating all the signs. The next term is 2. So I'm still going across the first row, and then that's pretty much it. Even though I could do expansion along any row or any column, but let's just do 1. So 2 is multiplied by what? Determinant of what matrix? Negative 1, 1, 1. Okay, and the last one is 1 times the determinant of what's left, negative 1, 0, 1, negative 1. Okay, so we know how to compute determinants here. So this one will be minus 1, right? I'm sorry, it's plus 1. It is just 1, yeah. So 0 times 2 minus negative 1 gives me a 1. Okay, minus 2, and this one is minus 2 minus 2, minus 2 minus 1, minus 2 minus 1. Okay, and this is 1 times the determinant is simply 1. Okay, so it is 1 plus 6 plus 1. All right, it is 8. Two very different ways, and the picture certainly captures all possible elements in an explicit way, while the formula that we used last is like I said, you can carry out the exact same way if you do expansion along the first column rather than the first row, or you can pick any other row, any other columns as well, as long as you take care of the signs appropriately. So, like I said, it is a sum of the determinants of sum of what? Sum of the products of 3 elements of the matrix, chosen in such a way that there is one row, one from each row and one in each column, with the signs. What do signs depend on? Depends on the nature of the permutation. There are 2 types of permutation, just like those orientations, whether or not they are they are even or odd. So that would take us would take us off if we were to talk about it. The thing that we need to know about, ultimately, the only thing that we care about in this course about determinants is this property over here. The matrix is invertible if and only if the determinant is equal to 0. So how it is computed, it is the second question. We don't really, either the way I just showed it to you or finding the inverse, nobody does it this way anyway. Okay, so if you are to actually get from just familiarizing yourself with this material into actual computations of these things, then that's not how they're done, because there are also computational issues, division by 0, 2 large numbers, 2 small numbers, and so on. So that's not how it's done anyway. So it's more important to know what these concepts are for, what the determinant is for, what is the meaning of the inverse function, and what's coming next is the eigenvalues and eigenvectors. So let's see. Let's take another look at let me just bring up that picture again with the stretching and shrinking. This is an example of one with that do the skewing, but it is a little bit confusing. It is better when so as you can see, the determinant is 1.5. The orientation is preserved as we have decided, but the stretching and shrinking of what we're looking at is, no, this is a rotation once again. So let's look at here it is. Okay, so this is a stretch and what is it? Well, it might not be quite clear. Let's just change it to something familiar, and like here. Okay, so let me do what we just did: 2 and 0 and 3 and 0. Okay. Yeah, it's not quite what I had in mind, but I hope it is clear that what has happened is a stretch. I guess I have to go back here and carry this out again. So 2, 0, 3, 0. Okay. Okay, so 2 stretches along the x-axis and y-axis separately, and it is when you see the matrix, you know what's happening. When everything is aligned with the x's, you can guess also that from the picture, but when it is not, like this, you might have trouble to figure out what has happened. So let's suppose we only care about stretching and shrinking in various directions, however. Then to determine where that direction is might be a challenge. because you saw that problem when you did the problem last week, the homework, that it looks skewed. It looks skewed, and it does not. Then it's not clear in which direction the stretching has happened. In fact, let me do an example for you with paint. Paint does it. Paint. Okay, so you can take a circle, Okay, that's a perfect circle. Okay, take my word for it. And then what I'm going to do is I'm going to skew it. So like this, and there is a resize, and there is actually skewing a possibility here. So you could stretch it. The first two entries, two possibilities, are actually about stretching. So let me do it anyway. So I put here 200 horizontally and 300 vertically. Okay. Okay. So that is a disproportional stretching. That is easy. Okay. Well, it doesn't fit, but well, yeah, I guess that tells you enough about what's happening. What I want to do now is skewing, and then the directions of the stretching are unclear. So if I'm doing this again, and now I'm gonna, where's the thing? Here it is. I'm gonna go to the bottom here, and I put here, I don't know, 30. Okay, so you could actually be wouldn't be too much of a mistake to start thinking that this is actually rotation. You can think about it as it was stretched horizontally and then rotated, right? It's totally perfect, but it is a skewing, and if you want to think about two stretches separately, then this is, you don't know where the direction is, okay? But there is a bigger problem that you may have seen in the past, and that is the problem with data. You may have seen this picture before. So suppose you have the XY axes, okay, and you have data. Well, data. Let's start here with the data. What if the data looks like, well, it could be looking like this, right? I'm trying to have like 100 dots here, but it could look like this. Does it look familiar? What? The circle, that one kind of data on the left, and the other one is on the right. So what does the right picture tell you? There's a correlation, yes. The correlation, and then how do you discover that correlation? And if you think about it, it is a linear algebra problem, because correlation meaning that x depends on y, by the way, or y depends on x. On x, which one depends on which, you don't know, it's data. But there is a dependence between them. You want to discover that dependence. How? Well, you need to find this angle. This angle or slope, and if you find the slope m, you'll say y is equal to mx. Okay, big discovery, right? So if you have a picture like that in your hands, then you can do it by estimation or whatever, but you imagine that you have, instead of 2 dimensions, you have 100, and then you don't have any picture, so you have to figure out that relation between maybe possibly 100 variables in a computational way. And then how? We will learn that how from looking at the two-dimensional situation, pretending that we don't know the answer. So what is the answer? The answer is, think about this. It is uncorrelated data on the left is transformed into correlated data on the right. Okay? Somehow by what? But probably by some kind of at its simplest, by some kind of linear operator, or linear, which is a factor. So linear operator. And so discover what the directions are. You do what we just saw. You just saw that picture is as if you have a circle here, an ideal circle here, and on the right what you produce is an ellipse stretched maybe in some particular direction like this. So if you we don't really want to think in terms of data, but we're thinking about the composition of our parameter curve, say, with our linear transformation, which produces a new parameter curve. Which that parameter curve is weird, and we want to figure out what it is. Okay, so what do we do? And the answer is you can see what's happening is we have to analyze f, and f stretches the plane in one direction much more than in the other. That's the key to this relation. So as you can see, that picture top right has certain width. It is a data, and there is some spread, but it has a width in both directions. But they're disproportionately the spread out is in the direction. What direction? This direction. In this particular direction is what you're trying to find. So if you find that direction, that gives you the relation if you ignore the width of that cloud. Okay, so, and that's exactly what we're after then. We want to understand if there is a linear operator, we want to understand what it means for how to discover in which direction there is a stretch and at what degree. Okay, so stretches the plane in two directions. Okay, so the question becomes how to find them. And the answer is actually uncomplicated, at least in the beginning. F v is equal to lambda v. Okay, so this is my vector v. This is my vector v. And then it has been stretched by a lambda. Whatever happens elsewhere, we don't know, but this one vector stretches, period. That's the initial step. And lambda is called the eigenvalue of the matrix. Okay.